Hi, my name is Ian Fogarty, and I'd like to talk to you today about polarity and its role in intermolecular forces. We need to investigate electronegativity. Electronegativity is the ability of an atom to attract electrons in a bond. So, for instance, if we had a hydrogen bond, the two electrons in this bond would be attracted to that hydrogen as well as that hydrogen. In this case, we're going to use a Pauling scale, and the Pauling scale, electronegativity of hydrogen is 2.1, and electronegativity here is 2.1. For this, the electrons here would be equally attracted to either one of these atoms because electronegativities are identical, so the difference in electronegativity on the Pauling scale is 0, which means this is perfectly shared. We would call this a covalent bond, a non-polar covalent bond. Turns out that a carbon-hydrogen bond, electronegativity of hydrogen is 2.1, electronegativity of carbon is 2.5. And so the electrons that are in this bond are going to spend a slightly more amount of time around the carbon than the hydrogen. And so it's not perfectly shared, but it's pretty close. And so the difference between these electronegativities is only 0.4. And so we would qualify that into this whole non-polar thing. So they're not perfectly shared, but they're so close that they behave like they are. And so they would be in this region right here, non-polar covalent. Now, if we go to something like oxygen and hydrogen, we have an oxygen bond and a hydrogen bond. Electronegativity of oxygen is 3.5. Electronegativity of hydrogen is 2.1, which means the electrons are going to spend more time around that oxygen than the hydrogen. That means this hydrogen is going to be slightly electron deficient and have a partial positive, not a full positive, but a partial positive, maybe like a 0.1 of a charge or something like that. And the oxygen would have a partial negative charge. This means the bond is still going to be shared, but the electrons are going to spend more time around the oxygen, and we're going to call that a polar covalent. So it's still being shared, but it's polarized one way. If we pick a hydrogen and fluorine, electronegativities are 4.0 and 2.1, then the difference between these electronegativities on the Pauling scale is going to be 1.9. And so that was going to fall right in this region right here. And that would be very polar. In fact, it'd be so polar that they're going to start talking about being stolen. And in Chemistry 11, we talked about the idea of being ionic, where the electrons are stolen from one element to another, and then one where they're covalent, where they're shared. And the reality is that it's really a continuum from one to the other. So suppose we compare a number of different bonds. Suppose we had one where the bond was very different in electronegativities, and so they were stolen. It's very extreme there. And then we have another one that's kind of right in there, where again we would consider them stolen, ionic. And here we'd have something very polar. And then over here we'd have something that is still in the polar section. I'm trying to run out of color, so we'll do a yellow there, and we'll do a fuchsia pink right there. And so the red and the blue would be both qualified as ionic. The black and the purple would be both considered polar, and the yellow and the pink would both be nonpolar. And so if you look at those categories, you would say that these two are most similar, those two are most similar, and these two are most similar. But if you think about it as a continuum, it turns out the blue and the black are probably most similar, and those two are probably most similar. So alkanes happen to be nonpolar. If we look at the electronegativity of carbon, which is 2.5, it turns out that alkanes are nonpolar. If we look at the electronegativity of carbon, it's 2.5. Hydrogen is 2.1. That's only a difference on the electronegativity scale of Pauling of 0.4, and that falls in the nonpolar covalent. And so this bond right here is nonpolar, that one is nonpolar, that one is nonpolar, and they're all nonpolar. So this is a nonpolar compound. And so here we have a carbon-carbon, so electronegativity of carbon would be 2.5 and 2.5. So those bonds, all the carbon-carbon bonds, would be nonpolar, and then there's the hydrogen bonds, hydrogen carbon bonds around there. They're also nonpolar, so this is going to be a nonpolar molecule. So what I'd like to talk about now is something called London dispersion forces, or some people call them van der Waals forces. And these are forces that exist between molecules. They're our first intermolecular forces. So we've talked lots in Chemistry 11 about forces that keep molecules together as a molecule, but we haven't talked very much about forces that keep one molecule attached to another. So here we have a hydrogen atom. There's my proton in the middle. We've got my little electron on the outside, and then another atom that's got a proton and electron outside. So this is two hydrogens floating around. And can we have one molecule attracted to another? Can we have one atom attracted to another? Well, it turns out that as this electron spins, it could be sitting here, and sure, it's going to be attracted very strongly to its own nucleus, but it also doesn't mean that it couldn't be slightly attracted to that nucleus there. And so there's going to be a strong force, electrostatic force between those two, and there's going to be a slightly weaker force attracted between these two because distance between things lessens the electrostatic forces. Well, that's great. As this electron continues to spin around, it's going to continue to be attracted to its own electron, its own proton right there. However, this electron can also be spinning around, and while it too is also very strongly attached to its own proton, it could be weakly attracted to somebody else's proton. And so there means that there's going to be a weak attraction from one to another. We want to look at boiling points and how intermolecular forces impact those boiling points. There are these bonds between molecules, London dispersion forces, one of them, van der Waals forces. And so this molecule is attracted to this other molecule. In order to boil, what needs to happen is this has got to vibrate back and forth. It's got to get warm enough to be able to break those, sever those bonds, and be able to escape and turn into a gas. Likewise, for this molecule to boil, it's going to have to break its bonds, lots of bonds to other molecules beside it. It's going to have to sever those bonds. It's going to have to move fast enough so that those bonds break and it can become a gas. So the intermolecular forces have an impact on the boiling points. It's possible to tell how strong the intermolecular forces are by the strength of the boiling point. The higher the boiling point, the stronger the bonds between them. If this is going to boil, this is going to have to vibrate so strong that it breaks its bonds to its fellow neighbors and is able to escape. If those bonds are weak, then you won't have to vibrate very much. You can do that at cold temperatures and the boiling point will be low. But if those bonds are particularly strong between this molecule and its nearest neighbors, then it's going to require a lot of vibration, it's going to require a lot of temperature, and it's a lot of energy in order to break those bonds and boil. So the intermolecular strength of the intermolecular forces dictates how strong the boiling point is, or the boiling point is an indication of how strong those intermolecular forces are. Now, if we have long chains for organic, here's our propane and our propane, and here we have 1, 2, 3, 4, 5, 6, 7. This is going to be heptanes. How does the London dispersion forces interact, and how does that change the boiling points? Well, if we have a molecule that has multiple atoms in it, then there can be multiple London dispersion forces. The electrons in this one can be attracted to electrons in that one. Electrons in this one can be attracted to electrons in those. And electrons here can be attracted to electrons there. And so you can have multiple London dispersion forces. And if we go to here, wow, there's just a whole bunch of London dispersion forces that go. So think about the boiling points. If you were to go and try and have this propane get away from another propane, you wouldn't have to break just one bond, you'd have to break 3 bonds. So you might have enough energy to break this one, but would you have enough energy to break those 2? And likewise for heptane, in order to break a heptane apart from its nearest neighbor, you'd have to break this one and all of them in order to separate it. So the boiling points are going to be higher as you go up in carbons. What we end up with is something like this, where you start out with one carbon way down here with a very low temperature, and it gradually increases and continues up. You end up with this nice curve where there's a dramatic increase in the boiling points, but then it gradually kind of levels off a little bit. Why is that? Well, way down here you have only one carbon, and so you only have a few intermolecular forces, whereas here you've got many carbons, and so the number of intermolecular forces go up. It's going to be harder to break all those bonds and cause more energy. But it's not linear. Why isn't it more like that? Because that would also show that as you increase the number of carbons, you increase the intermolecular forces and the energy required to boil them. Why isn't it a straight line? Why is it curved? If you go from one carbon to two carbons, that's a doubling of the carbons, so that's a dramatic change. If you go from 2 carbons to 3 carbons, well, it's still an increase, but it's not a big of a percentage. If you go to 20 and go to 21, well, yes, you're still increasing by 1 carbon, but the difference between 20 and 21 is not that significant, and so you have this leveling off effect. When you only have a few carbons, the boiling points are very cold, -50, -30. Then if you go to those kind of middle regions, you end up with C6 heptanes and hexanes, octanes, those are liquids. And as you get up into the C15s, those start to be waxes and those kinds of things where they're solids. Now, what does it look like for branched versus long chain carbons and London dispersion forces? Here you have 1, 2, 3, 4, 5. So this is a pentane, that's also a pentane, and you would expect to have intermolecular forces in here. Here you also have pentane 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it's got the same number of carbons and hydrogens. However, because of their shape, this little branch right here, they can't nest together as well. They can't pack as tightly together. And so there's a bigger distance between them. So yes, it's true, you can still have lots of intermolecular forces, but the distances between them are quite a bit. And the forces are proportional to 1 over d squared. If I double the distance, my force is cut into a quarter. And if I triple the distance, my force is cut by a ninth. Small changes in your distance have dramatic differences in your force, and the larger the distance, the smaller the force. So the shape of them, these branches, don't allow them to nest together tightly. I expect that this boiling point would be low, and that this boiling point would be higher. Even though the number of carbons and hydrogens are the same, these nest together much better.